Hello everybody. This is a voiceover of a presentation I made at a recent UCO conference, and I think it's a good introduction to the possibilities with CasADi. The outline is as follows. I start with an NLP, showing how to solve it in CasADi. Second, I go a bit more in detail about how CasADi works. And lastly, I show some recent additions to CasADi. Let's start with the NLP example first. So this is inspired by a simple physics problem. So we have 2 points that can move in a plane. A is fixed at the origin, P is free to move and subject to gravity. And they are connected with a spring. So let's give some characteristics of the spring. Let's say it has a rest length L and a spring constant S. And our goal is to find the static position of this system. So we can do this by minimizing potential energy of the total system, and the decision variables are the coordinates of the free point P. So decision variables are x and y in this case. So in the formula for potential energy here, you see first the part with the spring. So how should we read this? We have vector P and A. And if we take the 2 norm, we have the distance, so the length of the spring. If we subtract the rest length and we square it and times the spring constant, we have the total potential energy contained in the spring. The second part is just gravity. How can we solve this problem in CasADi? It's as follows. So we start by importing CasADi, defining some constants. Then we say we want a 2x1 decision variable P, which will hold the coordinates, the unknown coordinates. And then for A we need a 2x1 vector with zeros. And now we're gonna write pretty much the formula of the previous page. So we start by taking the 2 norm of the distance, the 2 norm of the difference of the 2 vectors. You can write it like this. And then the expression for potential energy. So once we have this expression, we can create a structure for the NLP. In Python it looks like this. So we create a dictionary with the X keyword denotes all the decision variables, and the F keyword must be a scalar expression that represents the objective. Next, we use the NLP sol syntax to create a solver instance. The first argument is just a label. The second argument is the numerical backend that we want to use, IPOpt in this case, and then the dictionary containing the symbolic primitives and the expressions. And once we have the solver object, we can call it, for example, with keyword arguments like this. So in this case, we initialize it with at position 2 - 1. If we look at the terminal, we see a printout like this, and this is printout from IPOpt. It's showing the different iterates, and it also shows a number of non-zeros in the Hessian. So here you see that CasADi was really supplying the gradient and Hessian information to IPOpt automatically. So the output of the call to the solver object is a dictionary again, and if you take the X part, you get the optimal solution in numbers. We can also use CasADi from Matlab. So let's take this Python example and see where we need to modify it for Matlab syntax. So the import statement becomes import CasADi.star. We have in Matlab index 1 based versus in Python index 0 based. So the y coordinate of the P, the point mass, is with index 2 in Matlab and index 1 in Python. So watch out for that. A dictionary becomes a structure. Call to the solver object with keyword argument becomes the classical Matlab approach. So two arguments really, first the label and then the actual value. And then the result of the solver call will be a structure in Matlab as opposed to dictionary in Python. So at this point I presented a way to go from a mathematical problem to a computer solution in a quite understandable syntax. Of course, this is not unique. You can use various packages to achieve this. So for this plot I worked with an optimal control problem with a one-state ODE, which I solve with single shooting, and it's the horizon length that I plotted on the horizontal axis. So you would expect that you get linear construction time for all the expressions when you want to solve such a problem. And it's not easy to achieve this. If you look at the other packages like SymPy in Python, or YALMIP in Matlab, or MuPath, the built-in symbolics engine of Matlab, you get different scaling behaviors. So what CasADi really likes to offer is having the flexibility of being in a real programming language and still obtain performance that is similar to a modeling language like AMPL. If we take derivatives, in CasADi we can achieve still the linear scaling because we do algorithmic differentiation. So here you see the construction time for the gradient, and it's quite easy to do it wrong and to get different scaling, as you see in the other packages. So let's move on with some internals of CasADi. First important notion is the expression graph. So when we write this line p equals mx.sim, we are really creating a node in memory that represents a symbolic variable. And the p variable in Python will just point to this node, really. Second line also creates an in-memory object, and the a variable is pointing to this node. When we take the difference, we see that a minus node is being created, which takes p and zeros as inputs, and the output of the minus node goes further to the norm2 node. So in this way you're building a graph of expressions. Actually, for this case there is some basic simplification because p minus 0 is always p, so it simplifies automatically. Next line we're gonna construct a bigger expression, so we subtract the rest length 1, we square the result, and we multiply with the spring constant and half value. Then we add the kinetic energy, so by taking a part of p, multiplying with gravity constant and the mass, and it's the end of this graph that is being pointed to by v. Then the dictionary is really just pointers to nodes again. So the X label expects the list or the collection of all decision variables, so it's pointing to P in this case, and F is an expression for the entirety of the graph here. So our graph has arrows always pointing in the same direction and no cycles. The nodes are matrix valued, and they also have some sparsity, and the sparsity needs to be known at construction time. And it's implemented with reference counting. Okay, let's look at derivatives. So we use algorithmic differentiation, both the forward and the reverse mode. So the first mode gives you really a Jacobian times vector product, and the reverse mode gives you a transposed Jacobian times vector product. And with these two primitives you can compose full Jacobians or Hessians. So in CasADi, when we had the V expression for the potential energy and P for decision variables, we can just call the gradient function or the Hessian function or the Jacobian function, and in the background AD is used to compose full expressions for these. Suppose we make our physical problem a bit more complex. So we have many points. So in this case, P will be a list of decision variables or symbolic primitives. And X will be the collection of all of them. So we simply vertically concatenate them in one tall vector with the vertcat command. And then, V is constructed in this for loop, but you don't need to look at the details. When we query the Hessian of the total potential energy with respect to all decision variables, this is possible, and what we see if we ask for the sparsity is that we get this banded structure. So that's a really nice thing. CasADi automatically discovers this structure, block diagonal structure, even though we never specified it should have this structure. So when I said it composed the full Hessian and Jacobian, it's really doing the sparse Hessian and Jacobian where possible. And this can give you speed ups. Because if you know the sparsity pattern in advance, you can group some things together. And you need actually less AD sensitivity sweeps to compute the whole thing. So this concept is this is done with graph coloring. And if you look into the domain of optimal control problems, block structure is all over the place. So it's quite critical to have this for optimal control applications. Okay, next concept in CasADi is functions. So if we look at this construction line, we see first is just a label E. Second is a list of symbolic primitives, in this case P, and then a list of expressions that we want as outputs. So in this case, the potential energy. So under the hood, or if you print E, you'd see it's a sequence of primitive instructions that relate to the graph that you supplied. And we have the virtual machine in CasADi, which is basically looping over all these instructions in sequence and then reading from and assigning to a work vector. You can see it printed with the @ symbol. In this case we had a work vector of length 10, but we can do better by recycling some parts of the work vector. So this is called working with live variables. So in this printout you don't see the counter going up to 10. So this makes it a bit more lightweight for the virtual machine. Now what can we do with functions? First thing is evaluate numerically. So E was the function object, and we can call it with some coordinates, 1 minus 2 in this case, and you get some number back. Nothing special. Well, what you get back is still a CasADi object. You can go to a NumPy array or a Skippy array in Python, or to the Matlab matrices in Matlab or in Octave. We can also evaluate the function symbolically. So in this example I've started with a symbolic primitive t and then created a 2x1 symbolic expression involving sine and cosine, and use this as input to our original E function. And then we could create an NLP that just depends on one decision variable, t, and the expression of before will still be somewhere in the graph. In fact, you see the graph here plotted, and E is a single node that points to the E function body really. Related to this is the notion of inlining. So on the left we have the graph from previous slides, and on the right we are inlining, which means taking the function body of E and expanding it into nodes and inserting all these nodes into the graph. In many cases the inlining is not what you want to do, because the graph on the right is much larger than the graph on the left, and often the size of the graph can be the limiting factor of large optimization problems. Another important notion is expanding. So on the left we start with a matrix valued graph, and then we expand each node into scalar primitive operations, and then you get the graph on the right. So we call this the MX graph and the SX graph. So for MX the nodes are matrices, sparse matrices, For SX, nodes are scalars. How would you construct it? In the script, you would just replace mx by sx. And then the p variable becomes a pointer to a vector which contains two symbolic primitives, p0 and p1. An alternative is that you still use mx, but then supply some expand operation to the solver or to a function in general. So mx is designed to be very general, and sx is designed to have low overhead. It's a bit like unrolling for loops, so often it's faster to compute it. Often you want the lowest level function to be an sx type. Let's look at some numbers. Let's take this physics problem with the multiple point masses, 100 of them. The cost to evaluate one Hessian for mx would take, in this example, 1.5 milliseconds. For sx, it would take a lot less. So this is an effect you often see. mx has advantages. Because it's general, you can insert like nodes that do a linear solve of a system, or a root finding problem, or an integration, or the expression graph functions that we showed before. For sx, it's just basic arithmetic and no function calls at the moment. Let's look at NLPs again. What is really happening if we construct an NLP solver? Well, in the background, you're creating expressions for sensitivities and constructing functions out of them. So in this example, we have the objective, we have the gradient of the objective, and we have a Hessian. And it's really these functions that will be called numerically by the backend, by IPOpt in this case. And you see the evidence for this in the printout of the timing. You see how many calls there were to the NLP functions, the helper functions. What else can we do in CasADi with NLPs? We can have inequalities and equalities, of course. So we do this by creating a G keyword in the NLP dictionary, which stands for constraints. And then when we call the solver, besides the initial guess, we can also supply bounds, in this case the upper bound for the constraint. Another thing we can do is parametric NLPs. So in this case, the mass will be a symbol, but it will not be a decision variable. It will be something that is fixed during optimization, but not known in advance. So in the dictionary for NLP, we use the P keyword for this, for parameter. And then when we actually solve, we need to supply a value for this parameter. So in this way, you could loop over a set of masses and then do some post-processing of the results, like a nice plot or something. The NLP solver object is really just another CasADi function. Like any CasADi function, you can print it to learn a bit more about it. In this case, it prints the input and output scheme. So that's a bunch of possibilities, and we only used a couple of few in the previous example. You have also the bounds on the decision variables, denoted with LBX and UBX, and you have labels for the bounds on the general constraints. If we look at the outputs, we don't only have the optimal value, but also multipliers, for example. There is also the possibility to pass options, and this holds for any CasADi function constructor. This is just an example for NLPs. So what is relevant for the IPOpt backend is, for example, the tolerance for solving, and you pass it as a dictionary again. And if you're interested in which options can I use, you should really look at the IPOpt documentation for this. There are other options that are CasADi specific, and these you can find in our documentation. So if you navigate to docs.casadi.org, for example, and you would click on the solvers list and click on NLP Sol, you get a list of possible options. Let's look now at how CasADi 3 is structured. So our code base is entirely in C++, modern C++. And we distinguish between the core and the plugins. So the core is all the symbolics that I explained, algorithmic differentiation, and the constructors for NLP problems, QP problems, and so on. And we have the plugins for a lot of numerical backends. The core is compiled into one single library, and each individual plugin is compiled into a separate library. And this allows us to see at runtime which solvers are present on some platform. So this is all C++. Now, how do we do interfaces? We do this with Swig. So we have one file that defines the interface, common to all interfaces, and Swig translates it into a Python interface and a Matlab or Octave interface. So that's the general architecture. In CasADi 3 we use one of the more advanced features of Swig, which is cross-language polymorphism, and we use this to allow embedding foreign pieces of code inside a CasADi graph. So in the C++ world we have defined a class called callback, which is just some CasADi function. It inherits from function, and it has several virtual methods. I'm only showing one, which is the eval function for numerical evaluation. When we go to the Python world, we could imagine subclassing this callback class and then giving an implementation for eval. So in this case, fetch some stock price. And then we could construct a symbolic variable, construct a callback class, and call it symbolically with the x variable. You could also supply derivatives and such. Of course, a stock price won't be differentiable, so this would just be for evaluation. A feature that matured in CasADi 3 is code generation. So why would you want to do that? For example, for portability. If you want to solve a problem online on embedded platforms, or if you're working in Python and want to go to Matlab, to some max file, you can use code generation. So whenever you construct a function from an expression graph, in this case f, you can just do .generate and you get a bunch of codes that you can call. Besides portability, it's also speed up that you can get with code generation. So you could manually compile the code and then use an external function to obtain it. You could also use the just-in-time compilation facility in CasADi. So this would be by just passing the JIT option to the constructor. So remember the example of before with 100 springs. We had a cost of 1.5 milliseconds for the MX graph, for the Hessian. If we JIT it, the time gets shorter. For SX also it gets shorter. And you can also supply optimization flags. So O3 in this case gives you even better evaluation speed. Now one thing you'll see when you try this feature is it's easy to bring your computer to a halt. This is because compiling, especially with optimization flags, is very expensive if you have a lot of code. And when you have a large graph, a lot of code is generated from it, and this chokes the compiler. So it's quite critical to have compact graph representations, especially for large-scale applications. The general idea is to work with a hierarchy of function calls, to chop your large problem up in smaller parts and then glue them together with MX. If I bring back the example with many springs, on the left I used a Python function to compute the expression for potential energy between 2 points. On the right I removed the Python function and created a proper CasADi function. If we look at the graph in memory, we're seeing all these pointers to the CasADi function, spring, which is called spring v. If we would do it with a Python function or Matlab function, we would get, instead of one node to a function call, we would get a lot of nodes. You can in fact get rid of the for loop also, and then you get a more compact graph even. So in this case we had Spring V, an object, a function object, and when you do .map on it, you get some kind of repeated application of Spring V. So if we have a look at the input-output scheme, you see that the dimensions of the input, which were 2 by 1, they are now 2 by 10, so they're repeated n times. How can we use Spring Map? We need to call it with a list of points to the left and a list of points to the right of each spring. So let's look at the code here. The first output, as I said, needs to be a repetition, so 2 by 10 in this case. We can do this by horizontally concatenating first point A and then all the points minus the last point. And the second input will be the concatenation of all the loose points, all of P. And we just call Spring Map with these two expressions. We sum it to get the total potential energy, and we add gravity, and we're done. So this gives you a more compact graph, which is better for jitting, for example. Instead of serial, you can also choose for parallel, for OpenMP. And there are also things like reductions. Instead of first calling and then summing the outputs, you could also ask for doing the summation inside the map node itself. There is also support for OpenCL pending. Actually, it was there in 2.4, but it needs to be ported to the 3 branch again. Thanks to this map node, we were able to do a parameter estimation problem with a quite large horizon of 100,000. And we were also able to use the GPU with OpenCL. So for some application, we got like 100 to 1000 speed up with a quite decent GPU. What else has happened in CasADi 3? So the health of the code has improved. You can see that the number of files has been reduced a lot. You can see that the lines of code has been reduced. But the ratio of documentation versus code has been maintained. So the code base should be in a healthier position at the moment. The syntax has simplified. It's not apparent from this presentation, but it used to be a lot harder. So now it's usable in plain master courses, and the users can focus more on formulation and trying out things. The code generation and the jitting has become mature, and there are some new primitives in CasADi like map and mapacume to replace for loops, and you can do some parallelization. And lastly, we have a new way to extend CasADi using cross-language polymorphism. Now, in summary, CasADi itself gives you the ability to do fast prototyping using symbolic notions, and you get a high performance when you evaluate the problem or its derivatives. And CasADi ships with interfaces to numerical solvers. It also ships some solvers itself, like IPOpt. And for 3.0, there was a major cleanup. Now, if you want to go ahead and try CasADi, it's easy. You just go to the install link and you select from the table which version of CasADi you want to try out. So the license is LGPL, so you can use it for commercial things as well. After you click a download link, you just simply need to unpack the zip file or the tar file and then add it to the path. So with Python you can do it with path append, or in Matlab with add path, and then you just import the package. So CasADi is not the end product for users. CasADi is made to build tools on top of it. For example, this is a language for dynamic optimization. You can just declare states and controls, declare the ODE, and you can start optimizing. So thanks to CasADi, you can write such package in not many lines of code and still be very fast. Other people have used CasADi, for example in JModelica. They have a collocation scheme written with CasADi, and there are a lot of publications using the software. For example, in robotics, in power generation with kites, MPC application, stochastic MPC, scenario-based robust MPC, all these things. Optimal experiment design, distributed control. Really, CasADi is just trying to help you to build this more complex analysis tools or explorations of existing applications. So that concludes my presentation. Thank you for listening.